The membrane research in NUS is one of the most internationally visible. For example, recently Lux Research has rated us as #1 in the use of membranes for water desalination and water reuse. Membrane research in NUS actually has been undertaken by many faculty members, covering different departments, different faculties. We have been very successful in getting over $30 million of research grants from industry and government sources since 2008.
One of my primary roles here is to coordinate the formation of a Membrane Science and Technology Consortium. There are 25 faculty members and 100 researchers working within the domain of membranes, and this consortium is an umbrella organization of those various activities. So within this consortium, there are 3 main research themes. The first is about membrane materials and fabrication. The second is about membrane modules and processes. And the third is about membrane systems and operations. So our vision is to really elevate the stature of NUS in the membrane science and technology area to a global stature. The mission is to make advances in novel materials and innovative processes within the domains of water, energy, and environmental applications, serving both the municipal and industrial sectors.
In the beginning, I really hate membrane. I consider there's no career. But the more I work, the more I found this is a very good area because usually you have to design the membrane a smart material. The second is energy saving. In addition, it has multiple applications. So I am working heavily on many areas. One is membrane for energy, natural gas or hydrogen separation. Another one is membrane for water and seawater desalination. Another one is a membrane for CO2 captures, membrane for biofuel separation and pharmaceutical separation.
In addition to separation applications, membranes are able to generate energy via pressure-retarded osmosis. PRO is a process to harvest the energy from salinity gradient. For example, at the river mouth, river water falls into ocean. Water permeates through the membrane from the low salinity side into the high salinity side to convert into hydraulic energy. Both flat-sheet membranes and hollow fiber membranes has been designed in our group for pressure-retarded osmosis. However, due to the mechanical property, hollow fiber membranes spun from phase inversion and interfacial polarization has gained more interest. They achieve a higher power density, which is 4 times higher than the commercial requirement.
Power evaporation is a combination of a permeation and evaporation process of transporting molecules through a semi-permeable membrane. It has unique advantages in the separation of isomers, isotopic mixtures, closed boiling point mixtures, and heat-sensitive mixtures. These are important industrial applications used in pharmaceutical, petrochemical, and food industries. In our research group, we have developed novel organic and inorganic hybrid thin-film composite hollow fiber membranes that surpass the performance of most polymeric and inorganic membranes. These membranes can be used in the production of biofuels and lower the production cost.
Our group's expertise is mainly in a combination of biological sciences and biomedical sciences with chemical engineering and environmental engineering. The technology we have today is to combine the approaches of chemical engineering with biological sciences. So what we are doing is to make a biomimetic membrane using a human protein called the aquaporin protein. We are planning to use this biomimetic membrane in an artificial kidney device. By putting these membranes that only allow water to go through at very fast rates, we are able to make the kidney dialysis machine as small as possible so that eventually it can become portable and wearable.
My research team designs innovative membrane bioreactors to deal with different kinds of organic pollutants, particularly high-strength phenolics in wastewater treatment. One of the bioreactors that we are working on capitalizes on the use of microalgae for tertiary wastewater treatment. That is the removal of nitrogen and phosphorus from treated water. In this setup, we use osmotic membranes to prevent cell washout, thus enhancing the microalgae concentrations, as well as an effective barrier to maintain good effluent quality of the water. This particular bioreactor setup can also be used to recover and recycle many important solvents that are used in pharmaceutical industries in Singapore. In biodegradation, you're using microorganisms to degrade the pollutants, and as a result, you're converting the pollutants into benign compounds like carbon dioxide and water. So bioreactors, which makes use of the microorganisms to treat the wastewater, is very promising and very practical.
NUS have been known to be fairly good in academic research. We are equally interested and receptive to do translational work. So we welcome industry collaboration of any kind, be it consultation work or small projects. We are here to help.